What we're going to do now is we're going to continue on with our discussion about the patterns that relate to the expression tree. If you recall, last time we had talked about what we were doing with the composite pattern, which we'll also be implementing soon in the assignment. What we're going to be doing now is we're going to be talking about the bridge pattern, which you've already got some experience with. You'll get more experience now with the next assignment, and we'll use it a variety of different places throughout the rest of the course. So the particular problem that we're trying to address here is how to encapsulate sources of variability in the construction and use of expression trees. So here's an example. Here you can see we have an expression tree, which is basically going to be holding a composite add node that has a leaf node with a value 3 and a leaf node with a value 4. So that's what's going into that particular construct right there. The nice thing about this, the nice thing about using what we're going to talk about here is we want to be able to hide a complex recursive structure, which is this composite, behind a simpler interface, one that doesn't expose all of those details. And that's what you really want to be able to work with. And once we have this more simple way of doing things, we can then use it to write other code that allows us to do things like traverse through the tree in various ways. So here's an example where we might have a begin factory that will return some traversal, let's say a preorder traversal just for the sake of argument, and it'll go ahead and keep traversing until you're at the end of the tree, and every step along the way we're going to say, please accept this item, this tree node, and go ahead and accept it and do something with it. So what's cool about this is if you look at that code, you'll see that you're working on an abstraction, which in this case is something called tree, which doesn't expose to the caller the complexity of the recursive structure of the composite. It's all very simple, all very clean. Notice also the use of the C++11 auto keyword, which deduces the type of the expression tree iterator, which is kind of cool. The second reason we want to be able to use what we're about to talk about is we also want to minimize the use of naked pointers. If you take a look at this code here, this is an example of how you might write some code to create your trees. In fact, you guys did this in your last assignment when you had the factory that you had to implement, the make tree factory. And the problem here is that if there is a bunch of code between many of these calls, really any of them, and where we actually clean the memory up, we're just asking for trouble because new can fail, something else can fail, and it might turn out that this delete operation is skipped altogether. So we'd like to figure out a way to try to automate the management of memory as much as we possibly can, because that'll clean up the amount of things we have to keep track of. Some of the other constraints and forces we have to like to deal with here is that the STL algorithms and containers all expect to have so-called value semantics. They want objects to work on, not pointers to objects. And what we've been dealing with so far have all been pointers to stuff, if you think about the way that the composite was structured. So what are we going to do in order to be able to address all these different design constraints? Well, what we're going to do is we're going to come up with a way that decouples the interface and the implementations. So we're going to create an interface class, which we're going to call expression tree, which you would call tree in your current solution. And that's the main abstraction that's going to be used by the client code, the code that's actually leveraging what we're producing here. And then we're going to have an implementer hierarchy rooted at component node, which is our composite, and that's going to basically have all the different variability involved here. That's going to have the different kinds of subclasses for leaf nodes and composite multiplication nodes, composite add nodes, unary nodes, etc. All that stuff is going to be hidden, and that's not going to be exposed to the clients. The clients aren't going to see that. And so you can use auto pointer or shared pointer or some other kind of pointer in order to be able to manage the memory of all this stuff. And we're also going to talk later about how we're going to use a factory pattern in order to be able to produce the right kind of implementation hierarchy. And we're going to be using, in our particular case, we're going to be using the builder pattern ultimately, but you could also use some kind of other pattern in order to do this. So here then is the main abstraction, and this is very much where we're headed with your upcoming programming assignments. We're going to have something called an expression tree, which we're abbreviating to tree, but it's the same idea. And here are some of the key methods that it defines. So some of the methods we're going to have here, and this is what your ref counter class is all about. This is all about managing reference counts. Why do we want to have a ref counter class? What's the thing this is buying us as developers?
Well, we don't have to manually delete it like as much.
as much.
It deletes itself when there are no longer any references to it.
Exactly.
So it simplifies memory management like we discussed previously.
Right. So the big win with reference counter class and the use of this pattern we're about to talk about is that it makes it so that you don't have to be responsible for keeping track of when something needs to go away. It keeps track of when it needs to go away, and when its reference count drops to 0, when nobody's using it, it goes ahead and deletes itself. So that's one thing. And we're going to see that we're going to have these constructors, the copy constructor and the regular constructor and the assignment operator and the destructor and so on, and they're all going to use our ref counter abstraction in order to clean these things up. We then have a bunch of accessor methods that forward to the implementer hierarchy. So these would be things like left and right and item. They return the appropriate elements that are needed for various purposes. And then we've got the accept method. I talked about that briefly before. We're going to talk about this much more when we talk about other patterns like visitor and iterator. We'll come back to that. And then we've got these traits, and we use these traits. We use the trait here in order to define our iterator factories. Now, if you are doing the grad version of the program, then you'll have iterator factories that look like this. If you're doing the undergrad version, it's a little bit different because you just have one method called iterator, I think, or create iterator or something like that. And that returns to you an iterator, whereas the grad student version has these pairs of iterator factory methods, begin and end, that create the beginning part of a range and the end part of a range. So there's a little bit of difference between the grad and the UGrad version. But the basic idea, the patterns are the same. The implementations are slightly different. From a commonality and variability point of view, the commonality here is we have a common interface for all the different kinds of expression tree nodes that we've got. And the variability is that we can have different kinds of nodes that are accessed by the common interface. So we could have a tree, but the tree could have lots of different expressions. It could have multiplication, division, subtraction, and so on. So that allows us to keep things much more consistent. Now, this particular way of arranging your software is given a name, and the name is the bridge pattern. And the basic intent of this pattern is to separate the interface from implementations, where the emphasis is on plural. So you want to have a common, stable, consistent, uniform, pick your favorite word that means consistent, stable, uniform, common, interface that is unchanged and static or fixed. And that's what clients program against, so things don't change. And then you want to be able to selectively vary the implementations so that stuff can be added later in terms of how the behavior actually works without changing the way in which the actual clients access the code. So that in a nutshell, that's the key idea. And people talk a lot about plug and play. This is a classic example of plug and play. So we're trying to find a way to have a same interface, plug in different implementations. You should apply this particular pattern when the interface and the implementation can vary independently. So you can have the same interface with different implementations. We'll see lots of examples of this in a second. And when also you would use this if you want to have a stable interface that you can have interchangeable implementer hierarchies. So we can actually replace the hierarchies wholesale without breaking the code that relies on this stuff. Here's a view of the structure of this pattern. This is one of the most fundamental design patterns, if you will, because it's really about common interface variant implementation. And that really is at the essence of good design. If you do your design right, often it's the case you can keep certain things fixed, certain things common, vary the implementation. What, again, is the reason we want to do this? What's the overall overarching force that drives us towards this? Why do we want to keep the interface common and change the implementations?
We can make changes more easily.
We can make changes more easily, and that's important because
Consumers want new features.
people want new features. You've got to port to a new platform. It just makes your life easier over time. Now, for a class project like this, it might or might not make life easier because you have to do some extra work to get that flexibility. But in real life, when you're doing something that has to live for longer than a semester, you'll appreciate the benefits that come from that. In our particular example, yeah?
I'm confused how this zipper structure can be adaptive pattern.
Oh, great question. So they're similar. In fact, one of the things you'll discover with Gang of Four patterns is that they all kind of look the same structurally. Almost every Gang of Four pattern has something on the left-hand side, right? And then it has something here, and then it has a hierarchy there, right? So they all look kind of like the same, and the adapter is no different. So there's got to be more than the structure that makes these patterns differ. So the adapter pattern is really about taking things that weren't intended to work together and making them work together. Whereas bridge is really about trying to be able to take things that have a common interface and then plug in different implementations. So in real life, you could combine these things. And the other thing I should mention too is that the bridge pattern is also often used in C++ in order to be able to handle memory management, whereas the adapter pattern doesn't deal with that at all. It's not part of its jurisdiction. It has no real effort on that. But they're both similar in that they take things and make them work together. It's just that with a bridge pattern, typically, you know what the common interface is, and you have various implementations, all of which have the same interface. If you have another implementation that you'd like to work with a common interface, you could apply an adapter in order to make it fit within the bridge hierarchy. But bridge is not, adapter is about trying to take things that were not designed to work together and make them work together. Bridge doesn't have that issue. It's not trying to make things work together that weren't designed to work together. It's trying to take things that were designed to work together and allow you to replace the implementations dynamically. That's the main difference. That's a great question. In fact, if you take a look at the Gang of Four book, you'll see that one of the things that shows up is a see also part. That's part of the structure. That's part of the form of the Gang of Four book, and the posted books that I've written have similar form. Oftentimes, the see also section will explain, how does this pattern compare and contrast with something else. So if you take a look at the see also section of adapter or bridge, it should say, this is like a blah, 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 and then you'll see some comparisons and contrasts. So there's the expression tree. That would be our interface. That's the abstraction that's common. And then here's the implementer hierarchy, which is rooted, as you can see here, with component node. And then we can have lots of different subclasses of this that do various kinds of things. So let's take a look at a simple example. This is very much like your solution, just a few tweaks. So here we have tree, which, as you can see, is parameterized by node or component node, as we say here, but in your case it would be node. And we would use some kind of shared pointer or some kind of ref counter like you have in order to be able to kind of manage all this memory. So here's the smart pointer. We have our own, but you could use boost smart pointer. This is going to manage the life cycle of what it's passed in, so it takes ownership and it is responsible for deleting it when it goes out of scope, etc. And then every call to the methods in the abstraction part, in this case the expression tree part, all the calls to the interface are delegated through the pointer, through the root pointer, through the smart pointer, to the appropriate implementation. Now this is really an important distinction. So it often turns out in the bridge pattern, if we go back here, that the operations that are defined in the abstraction portion are in fact non-virtual. They could just be regular old C++ non-virtual methods. Typically not static, but they're non-virtual. The methods over here, however, in the implementation hierarchy are in fact virtual. In fact, that's the whole point. You want to be able to come along and plug in different implementations, which will then, of course, delegate down to the appropriate dynamic type based on runtime dispatching of v-pointers and v-tables and so on. But this code over here doesn't need to have virtual methods. This is one reason why this works very well with C++ standard template library, because this stuff here is expected to have value semantics, and so you need to be able to have it copied by value, so you don't want to have virtual methods here. But if we play our cards right, we can have virtual dispatching through the implementation hierarchy, or the implementer hierarchy that occurs over here. And every method defined in the interface just goes ahead and forwards onto the implementation hierarchy through the bridge. This thing here is the bridge. So it's connecting those two things together. It connects the interface with the implementation. OK. You can take a look here, some links for more information about smart pointers and C++. Here then is an example of where we might use this. This is not the way I would do it, but it gives you a feel for it. Here we define ourselves an expression tree, and we initialize it with some subclass of component node. In this case, a composite multiply node, which has been initialized somehow. Yes, sir?
So is MVC using this pattern?
So, good question. So the question is MVC using this pattern? MVC is model view controller. The closest thing that the Gang of Four has to model view controller is the observer pattern, which is basically the view and model portion of model view controller. Controller sort of left out. And that's, if you recall, how model view controller worked, or how observer pattern worked. When a subject or a model is notified, it dispatches to a bunch of observers. So in the context of your question, model view controller, something happens, you have an interface that gives you some input, the model is notified, and it tells its various views. This particular approach is nothing to do whatsoever with model view controller. What might have thrown you a little bit maybe was the idea of forwarding and dispatching. But the main difference is that model view controller or observer has the purpose of notifying some unknown or untold number of observers or views when something changes, whereas in Bridge, when something happens, you're simply forwarding to the implementation to do the work. So model view controller or observer is about multiplicity. It's about multicast or broadcasting to a bunch of receivers, whereas Bridge is just forwarding. So it's a simpler intent. Yeah?
You said this wouldn't be the way you would do this pattern. Why? Is there anything
Oh, because in practice, I would most likely use some kind of factory here to make this thing. And in fact, that's what we're going to do in our programming assignment. What you did right now is you manually hard-coded that stuff. If you think about what you had to do when you wrote make tree for your assignment 4B, you had to manually write all those things out. Man, oh man, would you not want to do that in a real program, right? Way too much work. So what we're going to do, and we'll give you the code, is we're going to have an interpreter that you type a string like you would normally do, quote normally, you type a string, 1 plus 2 minus 3 times 4 or something like that. And the interpreter reads that, and it goes ahead and creates these things. So you don't want to manually hard code this. You want some interpreter, some kind of, an interpreter is basically a factory on steroids because it's parsing something to figure out what to build. And so you want to be able to basically create this by some other means than hard coding it. That's the main thing that would be different in practice. Yeah, good question. Other questions? So what are the good and bad things about this pattern? It decouples the interface from the implementation. Big win, especially in C++. Believe it or not, well, I'll talk about some known uses in a second. Implementers can vary dynamically. You can actually make this selection at runtime, or while your program is running, which hierarchy you want to connect into the interface, the abstraction class. That can be decided late using a factory or an interpreter or a builder or something like that. We can also use it for value-based STL containers and algorithms, which you'll be doing here shortly. The downside is that you have to have everything work with a one-size-fits-all interface. Everybody's implementation in this pattern has to conform to what the interface wants. Now, you can use adapters and so on to make that a little easier if you've already got stuff that doesn't quite fit, but it still has to have that one-size-fits-all interface. Lots of examples. C++ and Boost provide you with some built-in support for things like shared pointers to make this easier. Creating the right implementer, how do you figure out what implementation you want to be connected through the bridge? Factories are often used. This is not as widely used in Java as in C++, although it is used in Java, and I'll talk about that in a second. The main reason why the bridge pattern is much more used in C++ is because it's often used for managing memory, which is less important in Java because Java has garbage collection. There are plenty of places, however, where Java uses this pattern, and the most notable ones that I've been working on lately are many of the Java synchronization and scheduling mechanisms. So things like Java reentrant locks, Java semaphores, Java reentrant read-write locks, Java countdown latches. There's all these things that Java provides you for doing various kinds of synchronization and scheduling, condition objects, and so on. And they are all implemented using the bridge pattern internally. And that's because there's a choice in all the Java synchronizers between fair acquisition of these locks and resources versus non-fair. And fair always does things in FIFO order, and non-fair does it in any old hardware optimized way using low-level instructions like test and set or swap operations in the hardware. And so the constructors for all the various locks, the synchronizers that Java provides, will take a look at a parameter you pass called fair, and if fair is true, they will select a fair implementation. If fair is false, they will select a non-fair implementation. So it was kind of fun looking through all this Java code, because I'm recording videos about it right now, and looking at how they use bridge all over the place, even though they're not using it for memory management, which is why you would often use it in C++. Okay, here are some examples. I think I'll add another one just for kicks. So socket implementation, Java synchronizers, put that in there as well. ACE, if you ever get around to using ACE for some of your classes, you get a chance to play with that as well. There's an important design, yeah?
Oh, you have AWT up there. Is that what Java uses to create the window in Swing?
So Java used to have this thing called AWT, which is an older toolkit for doing windowing, which has been supplanted by Swing. But there may still be vestiges of AWT stuff floating around in there, and it also uses this particular pattern as well. But AWT is an older way of doing things.
Swing's definitely uses the bridge pattern.
I haven't played anything with Swing, so I can't speculate one way or the other. But if you were to Google bridge pattern Swing, you would undoubtedly find some uses. It's not uncommon in Java, it's just not nearly as common as it is in C++. Another reason for that is that in Java you typically use interfaces. Java literally has a language feature called an interface. And so separating interface from implementation is very simple in Java because you define an interface and then you say new blah blah where you have something that implements that interface. So bridge is kind of baked more into the language. And because reference counting is done, the garbage collection is done and reference counting is not needed, the need for the bridge to manage memory is minimized in Java. There are some cases though like synchronizers, socket implementations that use it. There's another very famous design principle called the open-closed principle that dates back to the end of the 80s. And you can take a look at this link for more information about the open-closed principle. The open-closed principle says design your modules, where a module is a class or a component or a set of functions or whatever, so that they are closed for reuse. In other words, the interface is fixed and doesn't change, but open for modification. In other words, you can come along and make new implementations. And so open-closed principle is a good way of designing software. The bridge pattern is a great way to implement the open-closed principle. So just connecting those pieces together. So here's a summary of what we've seen so far. We've looked at two patterns. We've looked at the composite pattern, which is really all about how do you define a hierarchy of different kinds of nodes based on their properties, whether they have one argument or two arguments, or what precedence they have, or whether they're addition, subtraction, multiplication, division, et cetera, or leaf nodes, and so on. That's what the composite is. And composite by itself is useful, but in languages like C++, where memory management is tricky, you're often better off encapsulating the variability provided by composite within the bridge pattern to get a common interface to encapsulate and shield the clients from the details, especially memory management details, of that variability. So these patterns are often used together. John?
It seems like the ref counter kind of violates encapsulation by having the use member instead of having it in some kind of wrapper for ref counter.
Yeah. You can certainly improve upon ref counter. That was just a quick and dirty thing to get it to work. But that's why I was saying shared pointer, which is C++ 11 and Boost's way of doing ref counting, is much cleaner. But then we'd have to introduce another thing and talk about it. So ref counter is just a simple way, and you also get a chance to practice writing a ref counter with incrementing and decrementing the ref counts. Bridge composite, which is what we're using in our next program, is a good example of a pattern compound. Remember I talked before about different kinds of patterns and pattern relationships. A pattern compound is patterns that are often used together, like peanut butter and jelly or something like that. So pattern compound would be bridge composite. You use a bridge for the interface encapsulation and uniformity, and you plug in a composite to be the implementer hierarchy. That's a good example of a pattern compound, things that would occur together. Okay, questions? So you will see, especially the grad students, are going to see lots and lots and lots and lots of uses of the bridge pattern for what is coming next. And we're just doing that because it simplifies the use of STL, and the graduate student assignment is much more STL-centric than the undergrad version. All right, next topic. How do we create these trees? So I've told you what a tree looks like, composite. I've told you how you access trees, bridge. How do you create these trees? Well, what we're going to do here is we're going to talk about tree creation patterns. And as you can see, there's a lot of stuff going on here. And this is a great example of where patterns play an absolutely invaluable role. Because if you didn't understand the patterns, and somebody came to you with a diagram that looked like this, your inclination, not unsurprisingly, would be, wow, this is very complicated and hard to understand. So if people just throw code at you and don't explain to you why it looks that way, it's often mysterious. It turns out that this particular way of arranging the code is actually a set of patterns that work together. This is what we might start calling a pattern sequence. So part of the code up here is going to be this thing called an interpreter. And as the name might suggest, the interpreter is going to read something, basically strings that define expressions in arithmetic form, and it's going to interpret those strings and do something with its interpretation process. What it's going to do is it's going to apply something called the builder pattern, which is another pattern we're going to talk about. And it's going to create basically a representation of the input string, the expression string, in something that's called a parse tree. So you probably haven't had a chance to learn about this yet. If you take the compilers course when it's offered here, you'll learn lots about parse trees. Parse trees are basically internal representations that keep track of various things, arithmetic operations, the structure of a program, an XML document, whatever, lots of different uses of parse trees. And we're going to create ourselves a parse tree that corresponds to the input, and then we're going to use the builder pattern to create from the parse tree the corresponding expression tree. And we'll talk a little bit later about why we decouple the creation of the parse tree from the creation of the expression tree. There's certain optimizations you can do, which you'll again learn about more when you take a compiler class at some future point. And what's produced by the builder are the nodes in the composite. And then those things, and I don't show it up here as a pattern, but it's sort of implied here, those things are then accessed via the bridge pattern. So what you're starting to see in a little baby steps is the creation of a pattern sequence, which are a group of patterns that often appear together. So I talked about pattern compounds. Pattern compounds are typically two patterns that are used together, like bridge, composite. A pattern sequence is a collection of patterns that start to get put together. There are many analogies for these kinds of things in everyday life. Anybody here ever take martial arts, like karate or things like that? Okay, so we have a few people. So when you start with martial arts, I took martial arts when I was in college. My little son is taking it right now. You spend a lot of time at first doing blocks and punches and kicks. Blocks and punches and kicks. You do it over and over and over again till those things become second nature. So a block or a punch or a kick is kind of like a pattern by itself, right? A pattern in isolation. So a block or whatever, that's a certain thing. And you do downward blocks and upward blocks and roof blocks and all these kinds of things, and you practice those. As you start getting better at blocks and kicks, you start to combine them together. Does anybody remember the name for what those are called? A kata, right. So a kata is a group of blocks and kicks. It's almost like a dance in some way. You're kind of doing it in a certain rhythmic form. That's kind of like a pattern sequence. So it's a front kick followed by a down block, followed by an up block, followed by a round kick, and you practice those things. And those are sequences of moves. So where we're headed with this stuff is this is already beginning to be a pattern sequence. So interpreter, which we use to create parse trees. We then traverse the parse trees using the builder pattern. The builder pattern is used to create a composite, and then we access the composite via a bridge. So those are four patterns that are now connected together to be able to describe the design of a portion of our overall solution. Now, this may or may not be very intuitive to you at this point, but as you get further along in building software and you start to work with other people, one of the inhibiting factors of success in teams is how do you communicate your intent to each other in an unambiguous way, in an unambiguous and intuitive way. So it turns out that once you've all mastered these basic patterns, you can talk to your team using patterns as opposed to having to try to talk to them in terms of implementation details. So once you've mastered enough of this stuff, you could say, hey, we need to write this code to read in some input and convert it into something that can be processed by another part of the system. And you could say we are going to apply the interpreter pattern to create a parse tree, traverse the parse tree, use the builder pattern, create a composite, take the composite, attach it to a bridge, and then that gets passed to something else. And you'll see later, our pattern sequence will end up doing things like having iterators and visitors and so on. So it becomes a group of things. And if you're building enough software in a particular domain, you will become fluent with the individual patterns and the pattern sequences, which are grouping them together. Just like a black belt in martial arts would obviously know a lot about punches, blocks, and kicks, but they'd also know about how those things get put together into higher order forms. Okay, stepping back from all that abstraction, let's take a very specific look at what we're talking about here. So the particular problem we have here is we've got some expression, and we'd like to turn this into our expression tree. So how do we do that? How do we automate that process to make this easy? And we'd like to do this in a way that really simplifies and centralizes these creations so we don't have to hunt all over the place, so we don't have to manually modify the code in order to make these changes. We'd also like to be able to do it in such a way that if we change the requirements later, where later could be the next assignment, we don't want to have to make lots of changes to our code. We want to be able to take the same pieces of code that we have already, more or less, and be able to modify them little or nothing, very little changes, in order to support other ways of expressing the input. So in-order expressions are one way. Pre-order, post-order, level order, those are other ways of expressing the input. And we'd like to be able to keep our solution open-ended with respect to the ways in which the orders are provided, and yet still be able to produce exactly the same trees that correspond to the appropriate traversal orders. Some forces, some constraints. We don't want to have to change the code when we make these changes to the representations, the new formats. And we'd like to be able to, this is sort of an obvious one, but your current solution doesn't do this yet. We'd like to be able to add new types of expressions without modifying the code, right? Right now, if you want to make a new expression, you have to go modify the make tree function. We want to be able to automate that. So you just type a string, or you read a string from a file, or someone types something in on a touch screen, and then you interpret it. So the solution here is to build an expression tree using an interpreter. That's the basic idea. And so here's kind of how this works. You have some kind of string. This is the string -5 times 3 plus 4. That's obviously an in-order way of doing things. And we're going to feed that into a factory that's going to go ahead and use an interpreter to parse the particular string and then create an expression tree that corresponds to that string. And so we're going to actually do this in two phases. We're first going to convert the expression using the interpreter into a parse tree. And then we're going to take the parse tree and we're going to turn it into an expression tree. Now, a good question to ask is, why do we go to the trouble of making this intermediate thing called a parse tree? What's the reason for that? What's the benefit of that? Well, in this particular model, we're just kind of mimicking or mirroring conventional ways people write compilers. And in most compilers, almost all compilers these days, they read the source language in C++ or Java or C# or whatever, and then they convert it into some type of parse tree internally, and then they do stuff to the parse tree, and then they create some kind of output. And that's often, it goes by various names, separating front end from back end, having an internal representation, blah, blah, blah. Why do you think people do this? What do you see as the benefits that come from having some intermediate form, as opposed to just reading stuff in and directly generating whatever you want? John?
Because if we have multiple ways to get to the parse tree, then you can have just one way to get to the expression tree.
Exactly. So that's one thing. So one thing, and I'll give you some specific examples, one motivation is if we have multiple forms of input that all create the same internal structure, by having one internal structure, we can have adapters that get from the different forms to that structure, and then from that point we can do one set of things to get to the other form. Can anybody think of some examples? This may be asking too much because you may not be that plugged into how compilers work at this point, but can we think of some examples of real-life compilers that work this way?
LLVM.
Right, so LLVM or GNU C++, GNU C. The GNU GCC stands for the GNU Compiler Construction Kit or something like that. It's basically a bunch of different front ends for C, C++, Fortran, Ada, and so on, that read the programs in whatever source language they are, and then builds an internal format, and then optimizations are applied to that internal form in order to be able to generate code for the backends. And the backends could be, Intel instruction set, PowerPC instruction set, ARM instruction set, goes on and on and on. So separating the input from the output, or from the representation from the final generated code, gives us a lot more flexibility. So that's a real-life example where you could have multiple forms of input. So that's one reason. What's another reason that you might want to separate the internal form from the final form? Yeah?
Shorten
You could change the final form. You could output in different ways. The example there being, Intel instruction set versus PowerPC instruction set versus the ARM instruction set. Those variabilities could just be minor syntactic assembly language transformations from the same common internal form. The other reason, yeah?
You could design your internal structure to be something that's very easy to work with.
You could design the internal structure like good examples, which they actually do. A lot of people use internal structures for these things that are very Lisp-like, because Lisp is very light on syntax. It's very simple syntax, and you don't have to think too much about it, just a bunch of parentheses. And so the internal forms can have that kind of a model, which is much less syntactically cumbersome than the syntactic form of C++ or Java or Ada or some other language. That's good. The other reason, which you're not necessarily expected to know at this point, is you can do all kinds of optimizations on the internal form. And if you share the internal form, you can reuse all those optimizations for all the different front ends. So there are lots of things you can do to optimize things that don't really depend on the specifics of the programming language, but can be done in a general way based on some internal form, some internal structure that's uniform and simple to work with. There's a bunch of reasons why it makes sense to decouple the internal form from the final form and the initial form. Okay, so this is the way we design this thing. We have this interpreter. We're going to give you the interpreter for your program. You don't have to actually implement it, but you'll know a bit more about how it works. We have some context, which we use for various purposes. In our case, it's for being able to get and set certain variables. And we use this to be able to have variables instead of constants for our leaf nodes. And then we also have some other things, which are really a hierarchy of symbols, which are used to make the parse trees. And the key thing I want to point out here is this method here, which you will have to implement, so it's important to pay attention to this, the build method. And the build method is used to build a component node corresponding to the expression tree node. So build is going to go from the view of things that is a parse tree oriented view to the actual form that we're going to use for our expression tree. So here's the commonality and variability part. We have a common interface for parsing stuff, and we can support many, many different kinds of variable expressions. Now, this particular way of arranging stuff is given a name, again. It's called the interpreter pattern. And basically, the intent of this pattern is to take some input, which is in the form of a language, and you have a grammar representation of this language, which, along with something called an interpreter, allows you to be able to interpret sentences in that language, which is kind of weird sounding if you think about it, unless you know compilers. Compilers, you give them input, which is called a sentence, and then they interpret or parse or process the input and do something. And the something, of course, depends on the language and the platform and all kinds of other things. The basic idea here is you want to be able to transform from one form to something else. You would typically apply this pattern if the grammar is relatively simple and stable, which mercifully in the case of expression trees is very simple and stable. They don't change a whole lot. And when time-space efficiency is not of paramount importance. If these things are different, for example, if you have a very complicated grammar, like the grammar of C++, or you really have to make this run super fast, you probably want to use some other technology, like a parser generator. Anybody know some examples of parser generators? Bison, very good. So Bison is a parser generator. Bison, you give Bison a program that looks much like a grammar description of a language like C++ or Java, and Bison will then generate for you some hideously bizarre code, which is basically a table-driven LR parser, which will then interpret strings or sentences in the language and tell you whether or not they parse. And believe it or not, the guy who developed Bison comes from something else called YAC, which stood for Yet Another Compiler, which was designed by a guy named Stephen Johnson a long time ago, back in the 70s. And apparently he was really enamored with the concept of LR parsing. And he would watch episodes of Star Trek and just build these tables, like, just drawing out stuff while he was watching Star Trek episodes and just drawing this stuff out. I don't know why that's important, but somebody told me that one time. I thought it was interesting. So that he was a fan of Star Trek. At any rate, he developed this thing called YAC. And so Bison, which is a play on words of YAC, is the free software's implementation of all this. And you typically combine Bison with a tool called Flex, which is a play on another tool called Lex. So Lex and Yak were the original tools, and Flex and Bison are the newer tools. That's all for C, C++ stuff. There's also something in Java called Antler, which does much the same kind of thing. And I'm sure there's a gazillion more things, yet more compilers and so on. So those are what you typically do for industrial strength languages with lots of complex grammar statements and expressions and constructs and so on. For simpler things, however, you can use the interpreter pattern. In our particular case, here's the pattern. You have this thing called an abstract expression, which in our case is a symbol. We have a terminal expression, which in our case would be a number or a variable. And then we also have so-called non-terminal expressions, which are things like add, subtract, multiply, divide, and so on. And there's actually a bunch of different ways to implement this pattern. The Gang of Four book talks about one way of doing it. We do something a little bit different using operator precedence parsing. There's a long, wonderful, rich theory of parsing stuff in computer science. So I'm just going to give you a little flavor of how you might implement this. Yeah?
Does this have anything to do with what we learned about in CS212, which was given a language to design a finite state automaton?
Great question. How does this relate to automata theory and automata and so on? There's a huge relationship. So parsing and lexing are really about automata. And so in something like lex and flex, for example, that is a finite state automata where you read characters one at a time, and you have a little finite state automata that tells you where to transition to for each thing you see. And whenever you collect enough characters, you can then go ahead and reduce them to a particular terminal or symbol, like an integer or a keyword or a token or something like that. That's lexical analysis. That's typically either deterministic or non-deterministic finite automata. A parser, like Yak or Bison or Antler, is basically a finite automata with a stack. And you can stack these things up, and you can push things on the stack, and you can pop them, and you can do reductions and so on. So that's all very much along the same lines. It's all about so-called regular languages and formal expressions and stuff like that. Yeah, there's a really cool theory of all this, and that's why they were able to build these tools, because there was an underlying theory that allowed them to figure out how to automate all these processing steps. Some parts of compiler construction, not to get too far off the point, some parts of compiler construction lend themselves very well to automated tools. Lexical analysis and parsing are two examples. Other parts of compiler construction historically were more ad hoc, like the optimization phase. But over time, people built up some really, really cool techniques based on discrimination networks and other forms of manipulating symbols and algebras in order to be able to automate the production of optimizers. So LLVM, GNU G++, GCC, and so on has lots of those cool things built into it. Here's an example of how you might implement the interpret method from the interpreter, which we're going to give you. So there's a method called interpret, and you give it the string that you want to be parsed, and it basically makes a parse tree, which is a list, an STL list of symbol pointers. And as it's parsing through each character in the input, so you can see here we have input, which is a string. We look at each character. If the input is a number, we go ahead and we treat this as a number. Else, if it's a plus, then we go ahead and treat it as an addition operator. Otherwise, if it's a left paren, we treat it as a parenthesized expression, et cetera, et cetera. So basically, you're parsing these things one character at a time, and you're figuring out what to do. So it's interpreting the input. And what it's basically doing when all is said and done is it's building up the parse tree with a bunch of symbols. And the parser has to know all the rules, and of course, it has to also give you the right input. Well, we'll talk a little bit more about this in a second. Some of the consequences: you want the grammars to be simple. If you have really complicated grammars, it's hard to do all this stuff manually. Every time you add a new rule to the grammar, you have to add another class to your design. The downside, of course, is it's difficult to do this manually, which is why people use compilers and parser generators and so on for real-life examples that are complicated. For arithmetic expressions, it's not hard. For something like C++, which is a very complicated grammar, it's not easy to do this. There's a bunch of different ways to implement this stuff. Your book goes into more detail. You can implement stuff as terminal expressions. These are the literals. These are things like a number or a variable or an operator. And then you can also have these things called repetitions or sequences, which are non-terminal expressions in the grammar. And there are lots and lots of examples that do this kind of stuff. various language processing tools, compilers, and so on and so forth. Okay, we're giving you interpreters, so you need to be vaguely aware of what it is, if for another reason that you need to know how to glue your code together with it, but you're not going to have to write it. This next thing, though, you will have to write. So this goes into the part you're going to have to do. So the next part of this thing is once we built up the parse tree, once we got the parse tree in memory, we now have to do something to it. And what we want to be able to do in our particular case for our expression tree program is we want to take the parse tree that corresponds to the input expression, and we want to be able to create from it the corresponding expression tree. So it's a straightforward set of things to do, and it turns out that a pattern can be used quite effectively to help guide the construction of the expression tree given the parse tree. And that pattern is called the builder. And the intent of the builder pattern is to separate the construction of a complex object. I think we'll all agree that an expression with the composite pattern is a complex object. It's got lots of different subclasses and objects and so on, and internal subobjects. We want to separate the creation or construction of a complex object from its representation so that the same construction process can create different representations. In our case, we want to be able to create different expression trees or different types of expression trees from different types of parse trees. And we want to make this as clean and simple and as localized as possible. So you would apply this typically when you want to isolate the knowledge of creating a complex object from its parts. In our case, we're going to build this thing bottom up from the parse tree that we've got. And you also want to be able to allow different implementations or interfaces for the object's parts. We don't show this in this particular solution, but you can imagine writing some kind of optimizer that would take the parse tree and do various kinds of optimizations like common sub-expression elimination, constant folding, other kinds of things in order to be able to minimize the amount of code that was actually going to be used for this. Here's the actual structure of this thing. You have something called a director, which in our case is the interpreter itself. You have a builder, which has a method called buildPart. We have something called symbol, which does that. And then you have a concrete builder, which is going to actually build a specific part. In our case, this will be the different nodes in the parse tree, like subtraction, addition, number, multiplication, and so on. And then the product of these things, of course, are, in our case, there are the expressions for the expression tree that we want. So here's kind of how this works. If you recall the earlier example we looked at over here, this particular code goes through the expression one character at a time, and it makes a parse tree corresponding to that expression. And when it's got that parse tree all built up, at the end, it's got a parse tree which is implemented as a linked list. What it does is it takes the parse tree, and then it goes ahead and the parse tree is implemented as a list. It says, give me the final element, the element that's at the end of the parse tree. I want you to build this thing. Now, what this is going to return is actually a composite, and it's going to take the composite and it's going to stick it into the interface from the bridge pattern. So earlier Danny had asked the question, what would you do other than hard code the creation of the composite for the bridge, right? And I said, well, hold on, I'll show you. This is where this actually occurs. So right there, parse tree, which is a list of symbol pointers, is going to go ahead and recursively build an expression tree, which is going to come back ultimately as a single component node pointer, which is the root of this arbitrarily complex tree of expressions. That's a factory pattern. And it's going to go ahead and stick it into an expression tree, which is the bridge pattern's abstraction. So we get back something that's been connected to be the bridge pattern. All the reference counting is handled properly and so on. But it's actually pointing to an arbitrarily complex expression. And here's kind of how it works. And this is what you guys have to do. So you can look at these slides to get inspiration, but you eventually have to sit down and build this part of the code. As you can see here, for each of the different kinds of nodes in the parse tree, we're going to have to build the appropriate kind of expression tree node that it corresponds to. So the multiply method in the parse tree is going to build a composite multiply node using the various pieces that are passed in from the expression tree. And again, when you look at the code, it'll make more sense. Leaf nodes are kind of the base case for the recursion. Oh, that reminds me, by the way, whenever you write recursive code, remember when your programming assignment for assignment 4B, you had the recursive traversals for pre-order and in-order and level order and so on. make sure that you stop. The several people had nothing that ever stopped. They kept calling themselves left and right. You know, they traversed left and right. There's no way to say, if the root is null, stop and print something out. So make sure you always put a basis case for your recursion. In this case, the basis case is the leaf node. So if we go to build a number, which is what this thing is, that will then go ahead and take the item that we will have gotten at this point, and it'll make a new leaf node for it, and that'll get returned as a component node. So just as an example, assume that our expression tree was just this little piece right here. Sorry, our parse tree was just a little piece. The parse tree would basically have an addition node, it would have an add node, and then it would have two other nodes which were number nodes. So as it was traversing this thing recursively, it would start at the top. It would start at the top over here, where it's a build. And the first thing it would do is, let's assume this says add as opposed to multiply. It would come in here and it would say new composite add node, left arrow build, right arrow build. That'll then be calling these things recursively on to build. And those would be number nodes. And so this guy would say, I'm a number node. I know how to build myself. I build myself with a leaf node. I return that. This guy comes back as a component node pointer from the left side. This guy comes back with a component node pointer from the right side. Both of those pointers are stuffed away inside the composite multiply node, or add node in this case. And that guy gets returned as a component node. Notice the beauty of inheritance to dynamic binding as used in this particular case, where we're creating a concrete node like multiply node or add node or leaf node, but we're returning these things as component nodes. And the reason that works, of course, is because of the magic of inheritance, because composite multiply node, composite add node, leaf node, etc., are all ultimately subclasses from component node. So that's the fundamental principle of object-oriented programming. Any questions about that? So you guys have to figure out how to put the right builder methods into your solution in order to build the right kinds of nodes. And this will give you a little hint. Consequences of builder. So we can use this to vary a product's internal representation. We don't really show that in this particular case. We're not varying anything other than we're varying the kinds of nodes that are created based on the input string that's passed to the interpreter. And we're also isolating the code for construction and representation. That's the real key benefit here. As you see when you look at the code, when you take a look at the implementation of all this stuff, you'll see that every subclass of symbol in the parse tree has a build method that is supposed to, when you implement it properly, create the corresponding type of node, which is a subclass in the composite pattern, which is the component node hierarchy. So all that stuff is being centralized and isolated, and it's all done in a common way. Once you kind of get the feeling for it, it's almost paint by number. But when you first see it, there's a lot of moving pieces. It can be daunting at first. And you can get very fine-grained control over the construction process because you're able to build all the various elements and sub-elements needed to build a complex composite. The downside to this pattern, and you'll see this also when you start looking at the code, there's a lot of subclasses. So for every different kind of node, we're going to have a different subclass. And so you start to kind of drown within a number of different things. And there's a bunch of issues, more physical issues as opposed to logical issues. Do each of these classes go in their own header file and their own implementation file? Do we put them in a common file? Those are design decisions that you have to kind of wrestle with from a physical design point of view. We've chosen one particular solution in our code base, but other people would do things in different ways, and you could compare and contrast the pros and cons of each approach. Lots of ways to implement this stuff. You can think about Builder as a member of the creational pattern family. So it's a factory, but it's a factory with a mission, and its mission is to build a composite, or not a composite, it could be a composite, an aggregate thing, a larger thing, as opposed to a typical factory. A typical factory just builds one thing. But this is sort of like a 3D printer, right? So a traditional factory, you have an expensive tool that's very carefully optimized to build one thing and one thing alone. Like it knows how to build Volkswagen rabbits or something like that. A 3D printer, in contrast, you give it a schema, you give it a blueprint, you give it an electronic document, and it tells it how to assemble those things. So the same tool can be used to build lots of stuff. So in some sense, you can think the builder pattern is able to build a more sophisticated thing than any individual pattern, a factory pattern by itself. But as I said, you can use it to create multiple things that relate to each other. There are a bunch of different examples of builder. A lot of compilers use them. It's very widely used. A lot of sort of toolkits and frameworks use them. If you take a look at the Gang of 4 book, they actually cite a paper that I wrote back in 1993 that I managed to get in there as a known use because I was reviewing the book as they were writing it, and I was writing this piece of code, and I was like, oh, this is cool. My service configurator framework, which is part of the ACE toolkit, which I worked on for a long time, it actually implemented exactly what's described in the pattern. And it was neat because I was writing that code as I was reviewing the book. So I was like, wow, look at this. You guys can cite this particular known use. Because I hadn't read that pattern before I wrote the code. So it was a good example of something being independently discovered by multiple people facing similar design constraints. So that's one of the other interesting known uses that you might find in the book as well. Not the world's most common pattern. It's typically used when you're trying to build complicated structures like composites and so on. OK, so to wrap up this particular section, interpreter and builder are patterns that are often used together. They don't have to be used together, but it's very common to use them together. And in our particular case, we're using them to create expression trees from much simpler representations of the input in the form of input strings, expression strings, like you would type in on a command line or something. As you can see, just literally by looking at the diagram that illustrates the code that we have here, there's a lot of moving parts, right? So if you didn't have these patterns, you would be drowning in a sea of classes. Once you have the patterns, you still may at first be drowning in a sea of classes, but the cool part is that you can chunk them at a higher level. So you're no longer, hopefully, looking at each of these things in isolation, but instead you're saying, okay, there's a group of classes that have some common themes, and we're using them in this way in this part of the design. And that's allowing you to abstract away from the details and to focus on design, as opposed to design as a bunch of low-level implementation details. I think I might have mentioned before, there's all kinds of examples of stuff like this. Common example people sometimes use is chess. If you're a chess master, Dan Fleetwood, our chair of EECS, is a chess master. And if a chess master looks at a game of chess, they see the pieces in a different way than a novice does, because they see the relationships between the various pieces at a higher level. And they'll say, this is Queen's Gambit opening or something like that. Whereas a beginner might just say, oh, look, there's a knight and a rook and a castle or whatever. And so these things are just individual pieces in isolation. I've also heard, by the way, that if you just randomly rearrange the pieces on a chessboard, then novices and experts are no better off. Right? The experts understand patterns of legal plays of chess, but random things, they just wouldn't ever expect to see them like that. And so that it's not meaningful to them. When an expert who understands patterns sees this diagram minus the patterns, they will also probably be like, oh man, that looks like a really complicated piece of code. The minute you overlay the patterns on top, they're like, oh yeah, I get it. Okay, that's a composite. All those things make sense. We're using a builder to make the composite. Yep, got it. We use an interpreter to make the builder, to make the parse tree, to use parse tree with a builder to make a composite, hide the composite behind a bridge. Fine, makes perfect sense, right? That's kind of where you should aspire to get. And obviously these are fairly simple patterns and only a handful of them. But in real life software, you have lots and lots and lots and lots of patterns. And so it is very helpful to be able to chunk them at higher levels of abstraction, because you can talk more effectively to other people. You can maintain the code better. You can guess at what the designer's intent was. And if the designer also understood the patterns that you know, and they followed the rules that are expected by someone who knows those patterns, wow, life is so good. Because now when you go to maintain that code or extend that code, you've kind of got some insight into their thinking. And you go, if they did it like this, they probably did it like that over there, because we were both using the same pattern. So it's kind of a cool way for things to work. Interpreter, builder, composite, and also I would add to this, bridge, as we see here, are a very powerful sequence of patterns. Okay, any questions about any of that stuff? So we have a few minutes left. I'm going to just start the next section real quickly. We'll probably come back and cover it next time. But I want to talk a bit more about the next programming assignment too. So what we're going to talk about in this next part of the module, or next part of the lecture, the pack of slides, let's take a step back. What have we talked about so far? We've talked about using Composite to get the structure of the tree. We talked about Bridge to hide that structure in a common interface. We talked about Interpreter to read an input string, to build a composite. We talked about Interpreter to read an input string and build a parse tree. We talked about Builder to take the parse tree and make a composite and then connect that to Bridge. So we've got all these patterns that we've talked about so far all kind of connected together. Now that we've finally got an expression tree, we want to do something with it. We actually want to process it. We want to run some actions or operations against the tree. And so that's what's coming next. So next we're going to talk about things relating to the use of traversing the tree and doing something to the tree as we're traversing it. As you can see here, just kind of looking ahead, we want to be able to write code, very simple code, using patterns that you are hopefully very familiar with by now. If somebody said to you, what pattern is this, what would you say? Iterator, right? It's obviously the iterator, so we're going from the beginning to the end. That's the iterator pattern, so that should give you a hint. It's an iterator. And you may not know this pattern as much, but you soon will. This is the visitor pattern. So for every element in this tree, we're going to visit each of its nodes one at a time and do something with it. So that's how we're going to be able to get actions combined with iteration.
Can you go over again how the build tree differs, the parse tree differs from the expression tree, and why you want to separate those two?
Sure. So the parse tree is really about the parse tree that we have is a fairly lightweight, simple representation whose purpose in life is just to keep track of the proper parsing of the string in whatever form it's in into some kind of internal representation. That's all the parse tree is doing. It's just there to kind of keep track of the various elements in the tree, like a symbol, add node, multiply node, subtract node, and so on and so forth. Once we've got things into that format, we could then go and do lots of stuff to it. What we're happening to do in this particular case is the stuff we're doing to it is we're going to go ahead and build an expression tree. But that's not the only thing we could do. We could also take that thing and do other stuff to it as well. So it's just as a way to be able to separate out the parsing from the later processing. That's the main difference. All right. So where we're headed here is this whole concept of, now that we have our composite, we built our composite with an interpreter and builder, we now want to take our composite, use it as a bridge, because that's what we're doing here. We're accessing this thing with the bridge pattern, and we want to be able to go and do actions and operations on it. And in order to do that, we're going to see the following sets of roles and responsibilities. So here's another diagram of our design. Once again, if you were simply confronted with this diagram, you might say, wow, a lot of classes, what the heck's going on? This is complicated. It's cumbersome. It turns out that some of the classes we see here are part of the iterator pattern, and we're also using bridge again. I don't call attention to it here, but it's there to deal with memory management. We use that a lot. But here's the iterator hierarchy, and as you can see, we have different kinds of iterators. We have iterators for level order iteration, pre-order iteration, post-order iteration, in-order iteration, and so on and so forth. Different ways of being able to iterate through the trees. And if you look in a little bit more detail, you can see that the level order iterator implementation uses a queue. In our case, we're going to use the queue you wrote just because we want to reuse it. In real life, you might use this STL queue. You can use the STL queue through an adapter, so it's basically the same difference. And then over here, for in-order, pre-order, and post-order, we're actually going to use the STL stack. We could write our own stack, but that would be overkill. There's already one in STL that is perfectly good. So those are the things we're going to use to implement our iterators. You're going to get a chance to write some non-recursive ways of traversing trees in different fashions. And we're then going to use, for the grad students, we're going to use the prototype pattern in order to build the iterators correctly. And for everybody, we're going to use the visitor pattern in order to be able to create a structure that decouples the actions we want performed on the tree from the way in which the tree itself is internally structured. So we're going to have different kinds of visitors. We're going to have print visitors and evaluation visitors and so on, all of which are subclasses of visitor. And those things are going to be used in conjunction with our iterator to walk through all the elements in our composite and then apply the operations, printing or evaluation and so on, in a clean and concise way. So the cool part about this is that the use of these patterns decouples the structure of the tree from the operations performed on the tree. So we now have an open-ended number of different kinds of actions we can apply or operations we can apply without ever affecting the way in which the tree itself is designed and structured. It's still a composite, still works the same way. We can add arbitrary actions to it. That's really, really powerful. It, again, may or may not seem that powerful at first glance. You'd have to really understand the alternative approaches to design and see these things unfold over time. But we'll talk about that next time. OK, any questions about this? What I want to do now, if there are no questions, any questions about any of the patterns we've talked about? So your 4 patterns that you've learned at this point, you should be responsible for knowing to some degree of fidelity, some of which you'll be implementing, some of which you'll be using, but you should at least understand more or less how they work. And then we're about to start talking about the iterator and visitor patterns. Iterator you should have a pretty good feel for because we've done iterators in STL. Visitor is by far considered the most complicated pattern in the Gang of 4 book. It actually isn't really that hard. It's just that there's a couple of moving parts. There are 2 parallel inheritance hierarchies, and there's use of both static and dynamic polymorphism, which are just scary sounding words. Try to figure out what they mean. But when all is said and done, it's actually pretty straightforward. We're going to walk through those things. There's a bunch of interaction diagrams you'll see that kind of step you through each of the pieces one at a time. It's the kind of thing where you've just got to sit down and look at the code eventually and puzzle it out. It's kind of like pointers. When you're first exposed to pointers, they seem really mysterious, and it takes a while to really grasp them. OK, what I'd like to do in the few minutes we have remaining here is go over and show you the next programming assignment. Let's go ahead and take a look at assignment 4C, which is what you're doing now. So what we're going to do in assignment 4C, as you can tell, make the font a little bigger, is we're going to go ahead and add in visitor. So that's the next main thing we're going to do. We're not going to put composite in yet. That's going to come last. But we're going to put in the visitor stuff. And you will have to figure out how to implement this properly, which at this point is not that hard, mercifully. But it gets you well set up for the next part 4, where it's a little bit more complicated. Let's take a quick look here. So for part C, what you're going to do is, instead of doing that recursive traversal or traversing with the strategy pattern, you're now going to be doing traversal with the iterator pattern. And that's why we're going to have to move away from using any form of recursion in our code to using non-recursive traversals of the structures using stacks or queues. The reason for that, of course, is that with an iterator, you want to give back things one at a time. Whereas with recursion, you start it in motion, and it's kind of like eating potato chips. Once you have one, it's kind of hard to stop, right? You just eat the whole bag. So that's why we're going to be using the non-recursive implementations of these things. So you'll have to iterate. You'll have to implement iterator, and we're going to do a couple of iterator implementations. And then you also have to implement visitor, which, as you'll see, is basically a generalization of strategy, which we use in conjunction with iterator to be able to apply these operations. So at the moment, you only have to be able to print the contents of the tree, although your design, which we've more or less given you, has to be able to handle other things. And you'll see that in the next assignment, because you'll have to handle evaluation as well. And you only have to define an iterator for level order traversal, which you ought to be pretty close to doing, because you did that hopefully correctly for assignment 4B with your queue-based implementation of level order traversal. You can now take that and use it as part of your iterator. But you should also make sure that your design, which we've largely given you, will be useful for other kinds of things as well, such as in-order traversal or post-order traversal or pre-order traversal, which we'll do next in the next assignment. OK, so those are things you can do. I would strongly recommend that you create a different directory and copy your files over there just so you don't have different things going on as you're getting reviewed comments and confusing the graders and so on. Yes?
So does that mean if we try and do like an ordered traversal, it should throw an unknown strategy exception?
The driver program shouldn't do that, but yes, it should at this point. Absolutely, yeah, that's fine. That's a good thing. That's a good solution. Let's see. So the key thing is, as usual, you've got a lot of code to look at. Make sure assignment 4B is working, especially reference counting, before you get too carried away with assignment 4C, because if assignment 4B isn't working, then you're going to get weird mistakes in assignment 4C, which is because assignment 4B didn't work. So we're really trying to get this whole concept of build on stuff and be confident in it before you start moving on to the next thing from a design and implementation point of view. And then the grad students have to do a little bit of extra work. They have to implement abstract factory, factory method, and bridge pattern. And the grad students also have the wonderful joy of doing STL iterators. Now, for those of you who are undergrads who whiz through this stuff really quickly, feel free to take a look at some of that stuff. It's really cool, but it is a little bit more complicated, so I recommend getting the undergrad version working first. Likewise, if you find assignment 4C too easy, start with assignment 4D next. It's more interesting because it really shows off composite, really shows off visitor in a much deeper way than what we're doing here. Okay, so to wrap up, keep working on your assignments, keep working on the reviews. All the reviews should be back at this point. If anybody does not have a review back for assignment 4B, let me and Will know, because we probably forgot to check it in somehow. But it should all be done, and so you should have everything that you need to get started on the next one.